Okay, here we go. So I'm going to show you pretty much how to solve these exercises in Agda. And so the first thing I just want to do is I just want to show you the GitHub repository here. So I think Martin showed you this yesterday already. So this has all the lecture notes as well as the exercises, the Q&A, the lecture log, everything. So for today, we're going to be looking at these exercises over here. I think some of you already had a go at this, maybe some of you haven't. But what I'll do now is I also put the solutions in the Git repository, so you can look at those if you want to. But I actually think it is much more helpful to see someone sort of live code these solutions so that you know how you actually arrive at these things, right? Because it's one thing to just look at the code, but the thing about Agda code is you sort of write this interactively. So the whole point is to see the interactions, I think. Also, let me stress, just for the people that join a little bit later, just, if you have a question, just speak up or put something in the chat and I'll try and keep an eye on that. Okay, good. Then the first thing I'm going to do is I'm just going to make a copy of the exercises, right? And just call them, I don't know, my exercises.lagda.md. This is just so that, if I ever update the Git repo, then I'm not going to overwrite these changes. I'm just going to make like a fresh copy. Okay, and then here we'll have to change the module name so that it matches the file name. So I'm going to do that, and then I'm going to turn on command log mode, which you won't have to do, but it's useful for you to see what I'm typing. Okay, especially with the Agda shortcuts. It's good to see that Martin was doing the same yesterday. So here on the right, you should be seeing this thing. So if I now hit Ctrl+C, Ctrl+L to type check the file, then you can see here that it says Agda2 log, right? It gives you the official name, but this is just type checking. Okay. And so we have this exercise sheet. I should stress that it's maybe a bit much especially for beginners, but it's sort of intended that way so that, if you're a little bit more advanced, then hopefully you're getting something out of this as well. And if you're just a beginner and you manage to do the first couple of ones, then that's fantastic. And that's perfectly fine. Okay. And okay, so let's get to one of these exercises just to get something going. So in the first one, we're going to define logical AND on Booleans. And actually, I said here that in the lecture, we defined it in one particular way, but in the end, we didn't get around to doing this. But it's really not so important. But what we're going to do, we're going to try and define AND here by pattern matching on both arguments. Okay, so we're just going to pattern match our way through and basically write down a truth table. So I'm going to go into the hole, and then we're going to do Control-C, which is going to case split, right? You can see here, make case. And it says pattern variable to case, right, at the bottom here in the buffer. Hope that's readable for everyone. And then I'm just going to type the variable on which I want to case split. So I'm going to type A and hit enter. And then you will see that the code has changed and it's given me these two cases, right, true and false. And I'm just going to align this a bit, and then I'm going to pattern match on B as well. There we go, just align it a little bit. And then in the second case, I'm going to pattern match on B. Now notice that I hit Control-C, Control-F here, which is for forward. So it makes the cursor move to the next hole from where the cursor is. So that's a shortcut that I'm going to use like all the time, and also Control-C, Control-B for backwards, which I just find very useful to sort of jump around the file a little bit. So I'm going to pattern match on B here. Just align this a little bit. Okay, and then should be fairly easy what to put here, right? True and true, this should be true. True and false, this should be false. And I'm just type in the hole, and then I hit Control-C, Control-Space. Okay. False and true should be false, and false should be true. And there we go. You can just kind of reload to give it the nice syntax highlighting. Okay, so it's just an exercise in case splitting, how to do this.
Sorry to interrupt you, but false and
ahead.
false should be false, not true.
Yes, sorry. I was thinking of equality, I think. Yes, sorry. Thank you. Okay, good. Someone is awake at least. That's great. Okay, so later on in the sheet, we'll sort of see that we could have defined this a little bit more, let's say, economically, right? We could have just pattern matched on the first argument because you can sort of write this a little bit slicker, right? So as soon as you know that the first argument is going to be false, you can just return false. So that's maybe a little bit more efficient, maybe a little bit more economical. On the other hand, this definition kind of looks like a truth table, so it's very easy to see what's going on. So that has that advantage. But we'll get to that later on. So here's another example of the XOR operation, right? So this is exclusive OR. So this only returns true if exactly one of the arguments is true. So again, just going to do the same thing. I can do Control C, case split on A, case split on B here, case split on B here, and then maybe, you know, clean this up a little bit so that it nicely aligns. And then we're going to say, well, true XOR true, this should be false because now both of them are true. True XOR true, true XOR false should be true. This one should be true, and this one should be false. There we go. Okay, good. And you can sort of proceed. And so Antoine's asking, true XOR B equals not B, false XOR B equals B. Yeah, definitely. That would be fine too, right? So that's another way of defining these things. Now, okay, let me make this point here. How you define things will have an impact in sort of when you start proving things about it. So on paper, generally you kind of skip over these details, but in Agda, you would need to sort of, you know, you need to be explicit about this. So it's going to make a little bit of a difference. Matthew's asking, with logical and defined by pattern matching on the first variable and defined by the truth, they will be equal. Yes, they will be equal in the sense that you can prove that if A and B will be the same, like will be equal to A and apostrophe B, right? So they will be equal, like up to identity type, but they won't be definitionally equal, right? Because the definitions are different. We'll get there in due time. You will be able to prove that if you like, maybe not in this session, but in some other session. Okay. Then there's some, you know, very similar sort of examples, but now with natural numbers, where again we're pattern matching. So for example, for the exponential function, and here we're going to choose to pattern match on the second variable only, right, on the exponent. So, you know, n to the 0 is going to be 1, and n to the successor of m, well, that should be the same thing as n times, and then n to the power of m. So I'm going to use this recursive definition, right? Martin also went into this in the lecture. And then we can sort of run an example here, right? So already, okay, this is important. So I moved to the whole here, and then I pressed Control C, Control comma, which gives me the goal and the context. Now here there's no context because there's no variables or anything like that. But the goal is, it already reduced it for, like, Agda just computed away, and it just says 81 equals 81. Well, we know that's the case, right? So let's just raffle 81, raffle for reflexivity, and there we go. And so we can sort of see, okay, at least they computed. Another way to compute would be to hit Control C, Control N, and then to give an expression. So for example, I could give 2 to the 3 here, and it should give me 8. And indeed, in the buffer down here, you can see that it gives me 8, maybe I zoom in a bit. Okay, that's another way of checking that. Excellent. Any questions about that so far? The pace okay? Too fast, too slow? Everyone seems okay. Okay, good. Use multiplication after Control C, Control N. What exactly? Okay, so let's do the multiplication question first. So can I do something like this? Yeah, you can. I mean, as soon as you have the function defined, you can try and normalize it. But in some cases, it will be very slow, but multiplication is quite simple. So it's okay, at least on low numbers. Wouldn't work for you. Okay, that's weird. Maybe we can try and look into that. message me on Discord or something like that. Right, indeed, Jacob was asking whether Agda will be able to infer the arguments of REFL. Yes, and it should almost always be the case. Yeah. Okay, so another function is factorial, of course. So here there's only one argument. So again, I'm going to pattern match. I'm going to hit Control-C, type in the n, and then here we go. So 1 factorial, sorry, 0 factorial should be 1, and this one should be the successor of n times n factorial. And now we just reload, and now it's unhappy here. It's actually good. So it's giving me this weird little thing because it's parsing it incorrectly. So we could fix this by setting some precedence for the operator, or we could write some parentheses here. But I mean, of course, I meant this, right? But Agda currently is reading it as successor of n times n and then take the factorial of that. And so it's complaining to me that this function is not being called on a lower argument. That's why you get this like orangey highlighting here. So I'm just going to write the parentheses and then that goes away. Okay, and then this one we could try and fill, but actually I could just hit Control-C, Control-A here, which is like saying to Agda, just guess what to put there, and it will give me REFL 24 because Agda just can figure out that that's the thing that should go there. Okay, now in a lot of cases, Control-C, Control-A isn't going to give you something useful, but in these cases, because it's so simple, it will be okay. Right. So then just going to move on to the next exercise. So this is a little bit more involved. So we're going to recursively compute the maximum of 2 natural numbers. So we're going to, have this function take 2 arguments. And we're going to say that the maximum of 0 and any number is just that number, right? Because 0 is the least number. And similarly for the other case where 0 is on the other side. And if I have 2 successors, then I know it's at least going to be like 1 plus, right? It's at least going to be the successor of something. So I'm going to take the successor and then recursively compute the maximum, right? And now we could try and define the minimum analogously to how we define maximum. So let's try and do this. And when we go into this hole here, just go there. You'll notice that currently I don't have any variables here, right? So one thing we could try and do is we could do like write this like nm here and then proceed from that. But actually, let me show you another way of doing this. And this will be especially useful if your function takes tons of arguments. So you could do Control-C, and then just hit enter. You don't write any variable name. And then what Agda will do is will introduce variables for you. Now, this isn't so useful in this case because you probably want to rename them. Probably don't want to call them x and x1, but the general principle is quite useful. And in some cases, when you've explicitly given a name in the typing over here, so if I'd written something like this, then Agda will take the same name. So it won't come up with silly names on its own. But if you don't give it a name, then it will come up with something like this. Okay, but I'm just wanted to show you how to introduce those variables. I'm just going to call them n and m now, and I'm going to reload. And now I'm going to go, and when I go into in the hole and I click on show me the context, I see that my goal is to produce a natural number, and I have 2 natural numbers in my context. Okay, now I'm going to pattern match on the first one. So 0 and m, well, the minimum of that should just be 0, right? So we fill it, Control-C, Control-Space, and there we go. And then over here, we have to have a little bit more information. So we're going to case split on m, and just align these a little bit to make it easier to read. Okay, so the successor of n and 0, the minimum of those 2 should just be 0. And well, the minimum of these 2 should be the successor and then the minimum of n and m, right? This is just as in the maximum case. Okay, so I'm going to write suck, and then I'll show you this other trick. So I could do this in a variety of ways, right? I could write the whole thing out like this, and just give it like that. Another way would be to say, well, I know I'm going to use suck, but then I don't quite know what to do yet. and then you put a question mark and you do Control-C, Control space, and it will generate another hole for you in which I can now write minimum and m and complete that hole. Okay, so that's the second way of doing things. Now, in this case, it's kind of simple, but you could imagine having a function, that you're not quite sure, you kind of want to apply this, but you're not quite sure what to apply to. And then it will be helpful to kind of do it in steps, right? So even you break this down into sort of an interactive process. I want to show you a third way, which is where I say, I want to use suck, but I don't really want to figure out how many arguments it takes or whatever. And so in that case, I do Control-C, Control-R, which is refine. And then Agda just automatically inserts holes for however many arguments it takes. In this case, it only takes one argument. Okay, so I'm going to do minimum and complete the hole here. Okay. Refine will be very, very useful when you have, higher order functions or functions taking, I don't know, 5 or 6 arguments. Then it's really nice that you can just say, I want to use this function, and I'm not quite sure what to put in the holes yet. I'll figure it out later, so that I can look at the goal and context and so on. So that's good to a good trick to be aware of. And then here we can do the example again. We can just hit Control-C, Control-A to get REPL3, and there we go. Right. Okay. Yeah, go ahead.
So presumably this is really inefficient, right, for big numbers. If
yes, yeah. So efficiency will definitely be an issue.
But I think what I found cool about HOT is that I saw an article that says that you can do a mapping between inefficient encodings like this, efficient encodings, and then they're isomorphic, and so actually the compiler could then use the efficient encoding instead of the inefficient one, which I guess is what's happening with the n numbers here, right? Because there's this pragma you can put numbers in, and then it uses the efficient one. Yes.
Yeah, you can use the built-in ones, which we're doing because we're importing this prelude from the lecture notes, and that's doing that.
Right. I think that's just worth pointing out, because a programmer who would think of Agda would think, oh God, but this is not possible to do any data analysis with this. So, but if the cool thing is that you can efficiently do proofs in one area and then transport them to an efficient space, then it becomes very interesting, actually.
Right. Yeah. So I mean, there's some papers, I think by Anders Moedberg in like representation independence and things like that. So if you're interested in that sort of thing, then definitely that would be something to have a look at. But yeah, I mean, for now, we're mostly concerned just to sort of get to know Agda a little bit and not worry too much about the efficiency, but definitely a valid point. Now, the next exercise is going to be to define a map. Now, if you've ever done any functional programming, then I'm sure you've seen this function before, because it's pretty much like, functional programming 101. If you haven't, maybe you're coming from a maths background or whatever, then what map does is it takes a function and it takes a list, and then you're going to just apply the function on every argument of the list, right? So you map of f of x1, x2, and so on. It's going to be f of x1, f of x2. That's the thing. So we're going to try and define this. So here I already have the function f, and I have the list x's, which I can see when I do Control-C, Control comma. I look at the goal, I look at the context, and of course I'm going to define this by pattern matching again, right? That's pretty much the trick for most of this exercise sheet and for a lot of functional programming in general. So I'm going to do Control-C, Control-C. I'm going to split on XS. So it's going to generate two cases, right? Either we have the empty list, or we have some list with something, something on the head. This is just the inductive definition of a list. Now, if I want to apply a function to the empty list, then all I can get back is the empty list. So I'm going to put empty list here and hit Control-C, Control space to fill this one. And over here, what I'm going to do is I'm going to apply f to the first element. And then I want to concatenate, right? I want to put this at the head of some other list. I don't yet know what list I'm going to put, so I'm just going to put a question mark, and then I'm going to go into the hold here. But of course, I now want to continue applying f to the rest of this list. So here's where the recursive call is going to be made. We're going to be saying map of f to access and fill that. And there we go. Right. So for example, if I apply the function +3, so this is the function that takes an argument and then adds 3 to it, to the list that is 1, 2, 3, then I should get 4, 5, 6 back. Right. I'm just going to hit baffle underscore here, and there we go. Okay. So that's just the map function, which I think many of you will be familiar with. Okay. So here's another one, sort of a variation on that theme, if you like, where we're going to define a function filter. So filter will take a predicate, which is a map from a type X to the Booleans, and a list, and returns a list. And the idea is that you're gonna select only those elements for which the predicate gives you true, right? So we're gonna select things from the list where the predicate holds. That's the idea we have in mind. So here it would be good to introduce some variables again, right? There's nothing in front of the equality sign, so I'm going to write p access here, and then we're going to load. And then once again, it's convenient just to get your hands on something to pattern match on the list. So I'm going to do that again, Control-C, pattern match on the list. Okay. Okay, if I'm going to filter the empty list, well, there's nothing to return anyway, so I'm just going to give back the empty list. And then here we're going to have like our first sort of to think a little bit. So what we'd like to do is we'd like to say, well, you know, try and see what happens when you apply the predicate to X. If it gives you true, then we would like to include it. If it gives you false, then we don't wish to include it. So we can use the if then else function to do this. We did this in the lecture yesterday. And so what I'm going to do is I'm going to write it like this. So this was the if then else function, like with the mixfix underscores, and then we're going to hit refine. Forgot one underscore. Sorry, if else then else. This makes no sense. If then else. There we go. And now I'm going to hit refine, and it will just generate all the necessary holes for me. Right. So there we go. Now I have 3 nice holes. So if and then the else clause, right? Okay, so what was the thing we wanted to do the case split on? Well, we wanted to see whether p of x was going to be true, right? So I'm going to hit p of x here. That's going to give me a Boolean, right? So if p of x, okay, in this case, I would like to include the element x. So I'm going to do x cons and then have to put something else, right? And so, okay, I'm going to include the element x, and then, of course, have to recursively go through the rest of the list, right? I want to make sure I filter the remainder of the list as well. So I'm going to do filter p x's, right? That's like the recursive call again. And if x didn't satisfy the predicate, then I'm just going to skip it and just continue with the rest of the list, right? And I reload, and that's it. Now, one thing you might like to do is you might like to do something like this, where you say where y_as is filter p x's, and then because this is the same expression occurring twice, so maybe you prefer to write it like something like this. Okay, does that make sense? It's just a matter of style. Okay, and so here's an example. For example, this predicate was going to say that a natural number is non-zero. And then if I want to filter the non-zero elements, then in this list, I would like to just return 4, 3, and 1. Now here, this is interesting. So I'm going to hit Control-C, Control-Comic here, and it gives me the goal. And then you'll notice it gives me this very weird 0 my exercises dot y_as is non-zero, blah, blah, blah. It's like it's giving me a thing that doesn't look very nice. What's going on here is that because I put the y_as into a where clause, it doesn't fully expand. So Agda's sort of just not inspecting what the where clause is doing, and that's why you have this dot y_as here. This y_as is the same thing down there. It just doesn't fully fully resolve it. Now, if you want Agda to sort of compute it a little bit more, you can, instead of doing Control-C, Control-Comma, you can do Control-U, Control-U, Control-C, Control-Comma. So you prefix it by Control-U, Control-U. And I'm going to do that now. And then it sort of says, you know, sort of really go at it. And then you notice that it fully reduces to this thing. Right, so this is actually, sometimes this is a downside of having these where clauses in that Agda won't compute the thing fully for you. And then here we could just put REFL underscore then. Okay, but it's good to be aware of this, that sometimes if you see something that doesn't really, you know, compute all the way down, you just hit it with a Control-U, Control-U, and then you get something a little bit better. Okay, we're just about halfway in the hour, which may be a good point to pause for some questions. I know there's a lot of questions on efficiency of natural numbers. I'm very sort of happy to leave that in the Zoom chat, or maybe take that on the Discord chat, and sort of take some questions, you know, and understanding the exercise sheet and the pattern matching and something like that. So if there's none, I will just continue. If there is some, now would be a good time to speak up. All good. Okay. So then let's look a little bit at the identity type. So first, we're going to sort of roll our own identity types, which is going to be specific for Booleans. So this is something that Martin was doing in the lecture as well, but then he did it for natural numbers. We're going to do it a little bit simpler. We're going to do it for Booleans. So the idea is, again, that we're going to case split these guys. So I've been doing that for quite a bit now, so I'm going to do it slightly faster. Go, just align this a bit. But now we're not going to give some Boolean output, we're going to give a type valued output, right? So true and true, true should be equal to true. So this should be the one type, right? The idea is that this is going to have an element precisely when these things should be equal. So true equals false, that should be not the case. So put the empty type here. Here we put the empty type as well, and here we put the one type. Okay, so it's just like Martin did in the lecture for natural numbers, except we don't need a recursive call because the Booleans are just very, very simple. And then we can try and prove that for every Boolean B, we can indeed find an element of this type, right? So that B is equal to B with this equality here. So again, you'll notice now if I do Control-C, Control-C, and I just hit enter, I don't case split on a variable, then it's going to introduce the variable for me. And because I named it B here, Agda is clever enough to name it B here as well. So that's kind of nice, especially when you have multiple of these, right? And then, of course, because the definition here is given by pattern matching, I really don't have any other choice but to pattern match here, right? In order to sort of get anything, I just have to do the pattern matching again. So I'm going to, oh, hang on. I'm going to pattern match on B, and here we go. And then, okay, now I need something of type 1, which is given by star, which Agda will be able to tell me if I just hit Control-C, Control-A. I can also type it using /star, but that's just the name we give to the unique element in the 1 point type. Okay, has exactly one element, and we call it star. Should zoom in a little bit, maybe. Okay. Now, we didn't actually get around to this in the lecture. The idea was to kind of go back and forth the this type that we defined, right? The one we defined by case splitting on the Booleans, and the identity type that we have in Martin-Löf type theory. Now, what I think I'll do is I'll skip it for now, just because we haven't really touched on the identity type either in Paige's lectures or in Martin's lectures. But maybe at the end of the session, I can come back to this if we have some time and just show you how to do this. Or you can have a go yourself. That's kind of up to you. I mean, it's not terribly difficult, but I think it would be better suited for at a somewhat later stage. And it's just that when I designed the exercises, this was obviously sort of prepared in advance of the lecture, so only afterwards kind of find out what was being covered. So let's turn to part 3, and also you can look at the solutions, of course, and seeing how this is done. Let's look at part 3, which is about proving some things in Agda, right? So all of the above, you can sort of kind of almost do in Haskell as well, just writing some, basic functions. But the nice thing about Agda is you can do some proofs. So for example, here is a proof that, if you do not twice, you're going to get back the same result. So we did this by pattern matching. So if I pattern match on the Boolean and I get, if it's true, then not true is going to be false, but then by definition, not false is going to be true, and then true is just true. Therefore, we put REFL true, right? And the same thing happens with false. Okay, so that would be an example of a very simple proof, and we can do the same thing here to prove that OR is commutative. Okay, so this is another nice trick actually. We can do this is alt dot to go to the definition of something, and then we can do alt comma to go back. Okay, so these are very useful. I don't know what the VS code bindings are, but I'm just going to show you in Emacs, and hopefully you can figure out or ask on Discord if you're using a different editor. But this is very nice to sort of go back and forth. So if I look at the definition over here, then we'll notice that this is somewhat clever definition, right? Because it says, well, true or anything is just going to be true, right? I don't need to inspect the second argument. And false or anything is just going to be the second argument, because it doesn't matter, right? You can just pretty much discard the one thing. So we're only doing pattern matching on one argument here. And that's kind of nice because it means that the proof is going to be a little bit, some proofs are going to be a little bit simpler. In this case, though, we'll probably have to do, we're going to have to do more pattern matching because the arguments are swapped, right? So if I just pattern match on A, it might get me something on the left side, but on the right side, we would still be stuck. Okay, but anyway, let's try and look at this proof. So I'm going to do Control C, and pattern match on A, and I'm going to go into this hole. And now you'll notice that here it says, so it's done some computation, right? So A is true in this case, therefore true or B is going to be true on the left-hand side, and on the right-hand side it says B or true. Antoine's asking a very good question, namely, is it possible to split on multiple variables at once with Control C? I don't know, actually. Let's try. Can we do this? Yes, there we go. Okay, I didn't know this, but that's good to know, right? So you can do Control C, and then A space B to just pattern match on them both. So thanks, Antoine. That's nice to know. There we go. We can just, if we want, we can sort of pattern match on all of them. But actually, I'm just going to go back just for the sake of, there we go. For the sake of, for pedagogical reasons, let's say. Because what I was trying to say is that the left-hand side reduced already to true, but the right-hand side hasn't really reduced to anything yet, right? We're still just looking at B or true. So that's why we would like to case split on B here as well, in which case, now we're just looking at true equals true. Okay, but that's easy, right? REFL true. There we go. And so similar here, REFL true. And then here the same thing happens, right? So you could, if you wanted, you could do this immediately by doing the double case split. REFL true. And then here, REFL false. There we go. So now we know that OR is commutative, right? The order doesn't matter. So that's nice. And then we could try and state and prove that AND is commutative as well, right? So this is actually sort of something new, because now you also have to put something here, right? You have to put something in a type. So I think it's a good exercise to try and do that. So what we would like to say is, we would like to say something like, well, for every A and B, right, for every two Booleans, which in Agda we write like this. If you really want, you could do like you could do like that, but I'm just going to sort of stick to more plain Agda syntax and just write this, right? And then you write the arrow type, and then we do A and B, and then triple equals. So this is backslash equals, sorry, backslash equals equals, and then B and then A, right? So we're just thinking of this as for all A and B in bold. Right, that's just how we're reading this, and then the proof will be exactly the same. So again, I can do Control C to just introduce the variables A and B. This time, whoop, hang on. This time, what's going on? This time, let's case split on both of them. There we go. And then, because I'm lazy, I'm just going to hit Control C, Control A in all of these, and it will figure it out for me. Right. So the idea of this proof is just you sort of unfold all the definitions and then everything holds by definition, right? That would be the mathematical proof. You would just say we inspect all the cases and all of the cases are trivial, done. And that's what Agda is doing for you. But the nice thing is that it's you don't have to unfold manually in a way, because that's what the computation behind Agda is doing for you. Okay, let's also have a look at this definition of AND, right? So this one is also clever, just like the OR. So this one says that if you have true and Y, then you just need to look at Y. And if you have false and Y, then you might as well just immediately return false, right? So this one is just on pattern matching on the left, okay? Right, so if you want to be extra lazy, can you type, so someone's asking if you want to be extra lazy, can you type -C in the hole before case splitting? Okay. Okay, I wasn't familiar with this trick, but when we save the chat for this, we'll make sure that this this gets a nice place somewhere. Okay, let's do this proof that this operation is associative, because it's good to see the difference in the two proofs. Okay, so here I'm just gonna can just introduce them, A, B, C. And here I'm going to try and be as minimal as possible. I'm going to try and do as little work as possible, in the sense that I want to have as least cases, right? So because this AND was defined by pattern matching just on the left argument, I'm going to try and just pattern match on the left argument. So over here, A is the left argument. So I'm going to pattern match on A and then have a look here. And then because this thing computes, it just tells me B, N, and C. Is it the same thing as B, N, and C? Well, yes, it is, right? Just by raffle. So I can just hit this with a raffle underscore and boom, there we go. And then down here, we're going to get even simpler. False equals false, right? Because as soon as A equals false here, this thing reduces to false. If false here, then this whole side reduces to false. And therefore, the whole expression here reduces to false. And so there we go, raffle underscore, boom. And the proof is done, right? So just a very quick, like, two-liner. On the other hand, this one, right, if you remember, the one with the prime, this one was defined by pattern matching on all of the cases. And so if I want to prove the same thing here, and I pattern match on A, and I look at this, then you'll notice that my goal hasn't really reduced at all, right? I can hit it with a Control U in the front, but it doesn't make any difference. It's just the same thing, because I need to do more pattern matching, precisely because this AND operation was defined by pattern matching all the way. So if I really want this proof to work, I'm going to have to pattern match all of them. And now things will be very easy again, right? You can just do these again. There we go. Okay, but you'll notice that this proof is maybe not as not as appealing as the proof above. But I think what's good to realize is that the definition you make, even though they're equivalent they're pretty much capturing the same operation. You can even prove that they are the same thing. They're just not the same definitionally, and therefore, when you prove things, you have to be aware of this. And some of your proofs might be longer or shorter depending on the definition you chose, right? So this takes a bit of experience and skill to try and figure out what's going to get you a good result in the end. And sometimes this comes back to bite. Yeah, so there's this trick where you do -c. So maybe we could try and do this. I didn't know this trick, so let's try this. So he's saying type this here, and then do before case splitting. Okay, so now I case split on.
You do Control-C, Control-A. No.
Oh, I see. Okay, like this. Ah, okay, nice. Okay, excellent. So that generates like the whole thing for you. Okay, so that you're saying when you put the -c there, it's going to do Control-C, Control-A, but before that, it's just going to case split on everything in sight.
It seems like it's slightly intelligent in what it does the case splitting on. If you try it on the previous example, it only splits on the A.
Oh, wonderful. Okay. So maybe it tries to case split on as least as possible and then see. I don't know. Okay, that's a nice trick. That's pretty cool. But in any case, the proof you end up with is a lot more verbose than the other one, right? But thank you for showing me that trick. I didn't know that. That's pretty cool. Okay, then we're sort of embarking on inductive proofs. This will be very, very common when you do Agda proofs, and it will be good. I think Martin did one example of this in the lecture yesterday, but it'll be good to see it as well, because this is just so typical for a lot of the Agda proofs that you'll see. So let me just take you through the proof here that max is commutative. So again, because max is defined by pattern matching, we're going to pattern match on the arguments to show that max of nm is the same thing as the max of m and then n. And in all of these cases, it's very, very easy, right? Because the thing just immediately computes. But if we're hit with two successors, so successor of n and successor of m, then things are a little bit more difficult. So I tried to make this proof sort of as verbose as possible. So I put to show here, just so that I could highlight the type again. So to show says that we need to show, right, that the successor of max of nm is the successor of max of mn, right? It has unfolded the definition of max, which then unfolds to just doing a recursive call and putting successor on the outside, okay? And then the idea is that I have this induction hypothesis because I can call maxes commutative with smaller arguments, right? I can call them with n and m, which is going to tell me that max of nm is the same thing as max of mn. And so then all I need to do is just to sort of whack successor on both sides of this equation, and then I'm in business. And that's what this AP is doing for me. So AP you can think of as action on paths, as is explained in the hot book, but also as on apply in a way. And so I sort of read this as apply successor to this equation, right? Just hit successor on both sides, and then there we go. So it'll be very, very common when you do an inductive proof to get some kind of, you get some kind of result from your recursive call, from your induction hypothesis, and then you want to use this somehow. And typically this will involve AP because you have some kind of sub-expression where you want to apply this, okay? So let's try and do this proof here. So I'm going to just introduce my variables here. And then I'm going to case split on both of them using the trick we saw earlier. Just align this a bit. Okay, well, these cases will all be very easy. And then here we do. So for clarity, let me try and do it in the same way as both. So I'm just going to have a where clause where I'm going to put to show, and then notice how I'm just putting these question marks everywhere, right? I'm not sure what to put yet, but I'll figure it out later. And then I hit reload, and now I have new holes. And now I'm using Control-C, Control-B to go between the holes. So I'm going to put to show here, just to remind me what I have to do. I'm the reader of the proof as well, right? Because I could just be looking at the goal and context when I do the proof interactively, but the reader would just be looking at the plain code. So here it's useful to do Control-C, Control-S, which is solve constraint, which is basically saying like, give me the unique thing here, right? I'm just asking for the type. Agda knows what the type is, so I'm just gonna ask it to do that. Okay, it is giving me this, which is actually not ideal because I know that min of these two things, right, is going to reduce. So I might as well just put successor of min and m here. It's the same thing, and you see that it accepts it just by definition of min. And the same thing here, but now with the argument swapped. There we go. Okay. Then my induction hypothesis, well, I'm going to call min is commutative of the smaller arguments n and m, and then fill in the type here using Control-C, Control-S. And then we'll notice that, you know, of course, this is very, very similar. So I'm going to do an AP. I'm going to hit refine. It's going to give me two holes, right? It says here is some sort of function. Can't really figure it out yet. And then here it says some sort of equality between two things, right? So these things are like meta variables, things that you hasn't really figured out, but you can see the equality here. So here I'm going to stick my induction hypothesis. Boom, there we go. And then here it says, okay, now you need a function from n to n. I'm going to put successor. There we go. All right, I'm just applying the successor on both sides of the equation. And there we go. Yes, Stephen, go ahead.
Hi, Tom. We learned yesterday during the lecture that in Martin-Löf type theory, there is essentially one recursion scheme for the natural numbers, right?
Yes.
So now we're essentially doing this these two inductive proofs on essentially tuples of two inductive numbers, natural numbers.
Mm-hmm.
So is there some kind of unifying induction scheme between this minimum and this maximum so that we can sort of factor the two proofs into one proof and then just plug in different sort of smaller things?
Right. That's a good question because the structure is very, very similar, of course. I suppose what one could do is you could sort of make a function that, like a generic function that kind of behaves like min and max, in the sense that, you know, it does something in these cases, doesn't really matter what, you can sort of parameterize that. But the most important thing is that it's going to apply something, right? In this case, successor, then just to a recursive call. So you could imagine a generic function that did that, and then you kind of instantiate max and min with this function with specific parameters. So for example, you sort of say, well, the first, you know, max should return, if the first argument is 0, it should return just m, whereas here it should return 0. So you kind of fit that out with parameters, but then the only thing that really matters, right, the recursive call, that part will be factored down into a generic scheme, and then you prove once that this function, you know, satisfies this kind of structure using this inductive proof. So you could imagine something like that. Does that answer your question?
Yes, it does. Thank you. Okay. I might give it a try if it doesn't.
Yeah, sounds good. That sounds fantastic. Yeah, so that's another thing that Martin was emphasizing, and I should emphasize as well. And I think also others like Dan Christensen and Emily Reels, you know, the best thing to learn is just to do, right? So this would be a fantastic thing to just try, and even if it fails completely, that's good because you will have learned something. Okay. So we're getting towards the end of the exercise sheet and also towards the end of time. So at least the time allotted for this problem sheet. So that's good. Would this also work for addition? Yeah, your microphone was quite high, Stephen. Thanks to you. Would this also work for would what work for addition exactly? Like an inductive proof or? Oh, I see, the general proof. Well, typically you would define in additional natural numbers not by pattern matching on both arguments, but only on one argument. So maybe, but probably not the best, probably not the most convenient way of doing it. Does that make sense? Because you're not pattern matching on both arguments there. Does that make sense, Mohit? hope that made sense. Yes, okay, fantastic. Okay, so let's I am tempted to skip this proof. You can just look at the solutions. It's not that interesting, but I would like to spend a little bit of time just on these two. So the map ones. And then if you have any questions about this proof later on, or whatever, just message me on Discord or message one of the TAs on Discord. Put a message in the Agda exercises channel, and I'm sure that we can help you. Okay, but just in the interest of time, I would like to do this one. Right. So map. Remember, it takes a function and it takes a list, and then it applies that function to every element of that list. And the idea is that it shouldn't be. It should be doing this in a nice way, somewhat. And one way of phrasing this, maybe you've heard of this term, is that it's a functor, which basically means that it preserves the identity and it preserves composition. Like that's all a functor really means. So the idea is, for example, for this is what I call map id, right? So the idea is that if you map the identity function on a list, you're going to get the same list back, right? So applying this identity function everywhere is not going to change anything, right? So this result is indeed what you would expect, and we can prove it by pattern matching again. Of course, we're going to pattern match because map was defined in terms of pattern matching. Therefore, when you prove it, you're typically going to be pattern matching as well. So here we're going to have, well, if I take the empty list, I'm going to get back the empty list. So that's just raffle empty list. There we go. And over here, maybe it's good to really write this out, or to sort of see what's going on. So it says id x, and then map id x axis equals x, and then xs, right? So that's, so maybe I should do show. Just going to write this down here so we don't forget it. So this is what we, hang on. Little glitch there. Okay, so this is what we had to show. So I'm just going to put this here. Okay, there we go. But now, of course, I think that's being a little bit silly here, right? Because the identity on X, well, that just simplifies to X, right? And in fact, if you go here and I do Control U, Control C, Control comma, then you'll see that it has reduced this. It's also reduced the map a little bit. Like it tried to write the identity as a lambda function. But okay, so we can just do this, right? And then we'll see that, okay, this is starting to look good, because on both sides of this equation, we're just adding x to something. So all we would really need is to show that this bit is equal to that bit, because then we would be fine. And so, of course, this is going to be another inductive proof, right? So I'm going to put an induction hypothesis here. Here I'm going to do map id of x's of the tail of the list, and just show you the type here by doing Control C, Control S, which tells me this. Okay, great. So what I'm going to do is I'm going to do AP. And now what is the function that I would like to apply? I would like to apply the function x, like add x at the front, right? So one way of writing this would be like this. So you can sort of, because this is a mixed-fix operator, I can specify sorry, it's an infix operator. I can specify the first argument and then just leave the second one as like a function, right? So, and then, so another, let me just put the whole here. So another way, put this in a comment below, would be AP ys, and then a question mark. Okay, that's exactly the same way of writing it. But it's just kind of nice that you can use the infix like this. And then here I need to show that map id of x's equals x's, but this I know by my induction hypothesis, right? So just put that down and I load the file, and Agda's happy. And this is the second part of it being a functor. which is that it respects composition. In other words, if I take two functions and I compose them, and now I map this on the list, then this is the same thing as first mapping the function on the list, the first function, and then mapping the second function, right? So you can sort of think of this operationally as if you go through the list and you apply the function f everywhere, and then you go through the list again and you apply the function g everywhere, that should be the same thing as just applying the composed function gf to every element of the list, just traversing through the list once, okay? And again, the proof is going to be very, very similar, except now I have these two functions f and g in scope. Notice how I made x, y, and z implicit parameters here, because Agda will always be able to infer them from the types of the function. And again, we do an inductive proof. And look at this. Okay, this case will be easy. And then here we go. Here we have to do some work, right? So what I would like to do is I'm just gonna copy this and then put another to show just for clarity. Show question mark. Put this here. It's now giving me some yellow because it doesn't know how to type, but as soon as I do this, it's okay. All right. So again, let's look at this. Well, you'll notice that if I look at this type and I normalize it a little bit, then you will see that G after F applied to X, right, take care, Stephen, is just G and then F of X. So I know I'm slightly overrunning, so I'm going to finish now. Put this here. Okay, and then put another here, right? We're going to do another inductive call here, like this. There we go, because so, doing this to the tail, we already know that the result is going to hold by the recursive call. And so over here, all we need to do is whack this gfx at the front of these things. So I'm going to write AP question mark and then IH. And then in this call, I'm going to do gfx once and then put this thing here. And there we go. Now there's, I think, 3 exercises that I left open for today, but we covered quite a bit of ground. So I'm hoping that was useful for everyone. I think people are starting to need to leave as well. So unless there's any really pressing questions right now, let's end the session here. Just let me know in chat if there's anything right now that you really need answered. If not, then message me on Discord or message one of the other TAs or start some discussion down there. And most important thing is to just to practice yourself with these things. So try and do some proofs yourselves. All right, I'm going to stop the sharing here and also stop the recording. So thanks for attending and see you in the next one.